In this class, we will continue the nucleon scattering. And we will discuss a more general scattering theory with a zero angular moment. And in the previous class, we have mentioned that when the energy of incident nucleons or when the energy of the projectiles or incident particles are very much less than 20 MeV, you can consider it as it is scattering with the L is equal to 0. So, incident particles are described quantum mechanically the incident plane wave. This was also mentioned in the last class. You can consider the incident beam as a plane wave and the scattered wave as a spherical wave. And mathematically, the incident plane wave can be described with the spherical waves because that is also a condition. You can write it as the plane wave can be written as a sum of spherical harmonics. So it is written as e raised to I kr divided by r and e raised to minus kr divided by r. By multiplying with the time dependent factor e raised to minus I omega t, it is easily recognized that e raised to I kr gives an outgoing wave, whereas e raised to minus I kr gives an incoming wave. You just imagine that the target that you can consider as the origin. And we have already mentioned that we are considering the center of mass system. So you can, of course, consider it as the origin. So you assume that your incident particles are coming from your left side. So your origin is here, and after scattering, it is moving to your right side. So it is like our x-axis. So to the left we have negative and to the right we have positive. So there your R is negative, here R is positive. That is why the incoming waves you are considering as minus and outgoing as positive. So for L is equal to 0, we can write the incident one as A by 2ik e raised to ikr by r minus e raised to minus ikr by r. And such an equation we have already used for your plane waves. And actually, you are considering it as a sine wave. And if you want, you can write a sine wave as, the equation e raised to I theta is sine theta, cos theta plus I sine theta. So e raised to I theta minus e raised to minus I theta divided by 2I will give you sine theta. So that is a way of writing this one. So we have mentioned that you have an incident wave and you have a scattered wave and a transmitted wave. That means it is going without any scattering. So we have considered the psi incident as it is coming and going. So the minus sign between the two terms, actually, if you want to consider, you can consider the total waves as the incoming plus outgoing. That's the total one. So normally our method will be the summing of these two. But actually what we are doing is, here we are putting a minus sign. The reason is that at r is equal to 0, that means at 0, the incident wave function must be finite. That is one condition. That means your incident wave is a finite one. That means its amplitude is finite. So when r is tending to 0, you can see that this is becoming infinity and this is also becoming infinity because you have divided by 0. A number by 0 normally it is undefined or infinity. So if you are putting a plus sign here, it is infinity plus infinity. So in order to avoid such a confusion, if you put a minus sign here, it is okay. Infinity minus infinity is not an infinite term, it is a minimum term, that is it may be a 0. So, and using the coefficient a for both terms sets the amplitudes of incoming and outgoing waves are equal. This a is the amplitude of incoming wave and the outgoing wave. So, in other terms, you can consider as when you consider only the scattered and you have incident, and that from that incident you have scattered as well as transmitted, and that transmitted is the part of your incident. We further assume that the scattering does not create or destroy particles, and thus the amplitudes of the IKR and e raised to minus IKR terms should be the same. All that can result from scattering is a change in phase of the outgoing wave. So, after scattering, you can write it as A by 2ik e raised to I kr plus beta by r minus e raised to minus ikr by r. And actually this is your incoming part. So, this is the case before scattering, or if you have no scattering, this will be the condition. And in scattering, you can say that due to scattering, there will be a change in phase, not amplitude, change in phase for the scattered wave, and you can consider the phase as beta. So, this positive term becomes e raised to I kr plus beta, and this is the incoming part. If we want to find out the amplitudes of scattered wave, we need to subtract the incident amplitude from psi r. So, psi scattered is psi r minus psi incident. So, this is psi r and this is psi incident. In terms of psi scattered, the current of scattered particles, the meaning of that term is that this number of scattered particles per unit time. Normally, you are defining electric current as number of charged particles passing through a point in unit time. That is why these scattered particles are actually moving, or they are scattered. So, through a point or through a particular point, if a number of these scattered particles are moving. So, in unit time, how much number of particles are scattered through a point? You can consider it as a scattered current or current of scattered particles. And if you consider that current by area, you have the term current density, which is defined as current by area. So, the current of scattered particles per unit area is the current density, and it can thus be calculated by the following equation. And this is a standard equation. You have to know that equation, and that is the condition. J scattered is h cross by 2im into psi star dou psi by dou r minus di psi star by di r into psi. Again, J scattered is h cross by 2im psi star di psi by di r minus di psi star by di r minus psi. And this is an equation from quantum mechanics. The scattered current is uniformly distributed over a sphere of radius r. You can visualize that. That means scattering can be in the forward direction and maybe in the backward direction also. So it will be in a it will be distributed over a sphere of radius r, and the probability d sigma that an incident particle is scattered into d omega you are considering as a solid angle, is the ratio of scattered current to the incident current. That is clear. The if say 50% of half number of particles are scattered in a particular direction or in this solid angle, and you have a say n number and n by 2 is scattered in the same direction, you can say that the probability of scattering is 50%. That means n by 2 by n. And so that is a way of calculating this. Is the ratio of scattered current to the incident current. So you can write that d sigma equal to j scattered by j incident into r square d omega. And actually you have an incident current and scattered. So that will give you the ratio of scattering, and that scattering will be in the whole one, and normally it is in the whole area. So through a particular area, actually this is the area of a on the spherical surface which is subtending an angle d omega at the origin. That is this area r square d omega. And the differential cross section you are defining as d sigma by d omega, which is the probability per unit solid angle, and can thus be written as d sigma by d omega is r square j scattered by j incident. So these equations are known to us. That is why we are just mentioning them. And now we will be substituting the values. That means it's j scattered and the j incident can be find out if you know the value psi. So we are trying to extract or to evaluate that value psi, and we will be substituting them, and we will be doing some mathematical calculations to get this value. So that is the aim of these using these equations. And this we have already, this is what we have mentioned. You have some plane waves, and after scattering you have the spherical waves, and that spherical waves are scattering into a spherical surface, and at an instant let r be the distance you are calculating, and at that r you can see these arrow marks. They are the scattered ones, so they are, it's a direction of scattering. So as time lags or time increases, the radius also increases. So on that sphere you can consider a small area, and it is subtending the solid angle d omega. So this you have the equation that solid angle equal to area by r square. So solid angle equal to area by r square, or area equal to r square into solid angle. So that is why you can consider this as r square d omega. So taking the equation 5, and equation 5 we have already done in last class. There, for the region small r greater than capital R, the wave function we are getting as, this was the equation we got, ur equal to c sin kr plus delta. And here, in place of that delta, we are using delta 0. This delta 0 means that we are considering the scattering with L is equal to 0, and this delta is the phase shift which is caused due to scattering, and if it is for L is equal to 0, you can consider it as delta 0, and that is actually not mentioned here, but you have to know it. So that is why you are writing it as delta 0. So UR is C sin KR plus delta 0, and you can write psi R as UR by R. So it is C by R sin KR plus delta 0. And this form can be manipulated in the following way. Actually, it is a manipulation. Psi R equal to C by R sin KR plus delta 0. So you can write it as e raised to I of KR plus delta 0 minus e raised to minus I KR minus delta 0 divided by 2I. This 2a can be taken here, and also you have e raised to minus I delta 0 as common factor, not plus I minus I. So when it is taking minus I, this product should be I KR plus delta 0. That is why it is e raised to I KR plus 2 delta 0, and here it is e raised to minus I KR by R. So you have an equation. And already, so this is the equation for psi r, and already we have made an equation for psi r with the knowledge of your incident wave function, and there we have assumed that you have a phase change of beta. So from equation number 10, we have written as psi r is a by 2ik e raised to I kr plus beta by r minus e raised to minus I kr by r. So you got two equations, and now you can compare them, and you can see that this beta equal to 2 delta 0, and this a by 2ik equal to c by 2I e raised to minus I 0, this second one, and from that you can write as either a as kc e raised to minus I delta 0 or c as a by k into e raised to minus I delta 0. So which value you have to use, a or c? You can use these equations. And now by subtracting the incident part of the wave function from equation 15, we have the scattered wave. This equation we have already written. Psi scattered equal to psi r minus psi incident. So this psi r means it is the wave function after scattering, and after scattering it consists of the incident flux or incident particles as well as scattered particles. So in order to find the scattered one, you are subtracting the scattered wave function. From the scattered wave function, you will subtract the incident wave function. This is the total one after scattering. So this contains incident as well as scattered. So in order to find the scattered one, you will be subtracting psi incident from psi r. You have the equation for psi r as 2 by c by 2 I e raised to minus I delta 0 e raised to I kr plus 2 delta 0 by r minus e raised to minus I kr by r minus a by 2 ik e raised to I kr by r minus e raised to minus I kr by r. Now you can substitute for this c as a by k e raised to minus I delta 0. Already you have e raised to I delta 0 minus I delta 0 here, 2i is here, and these terms are here. So initially this and this cancels. So it is a by 2ik, which is common factor. So a by 2ik, the first term e raised to I kr plus 2 delta 0 by r. This is e raised to minus I kr by r, and minus of e raised to I kr by r, minus and minus becomes plus. So plus e raised to minus I kr by r. So this and this get cancelled. So you have a by 2ik e raised to ikr plus 2 delta 0 by r minus e raised to ikr by r, or taking this r outside. Your psi scattered you can take as a by 2ik, and of course this e raised to ikr is also common. So it is e raised to 2I delta 0 minus 1 e raised to ikr by r. So we got an equation for psi scattered. And now you can substitute this equation. We have the expression for psi r as well as psi ir. We can substitute them to find out the current, scattered current density, and also we have the incident current density. And by substituting J scattered by J incident into R square, you can find d sigma by d omega. That is the your cross sections, total cross section, etc. And that we will do in the next class. Thank you.